Pluto is a distant and mysterious dwarf planet that was once a member of our solar system's planetary family. However, recent startling announcements by leading astrophysicists Neil deGrasse Tyson and MIT's Michio Kaku have brought Pluto back into the spotlight with a shocking revelation. They suggest that this icy world is on a potential collision course with Neptune. But how could this happen, and what would be the consequences of such a massive event? Are we witnessing a rare astronomical phenomenon, or is there something more to this impending cosmic collision? Join us as we explore the possibilities of a Pluto-Neptune impact. Pluto, a former planet that was demoted to a dwarf planet partly due to its peculiar orbit, remains a subject of fascination and study in the astronomical community. According to recent predictions by leading scientists, Pluto's trajectory is dangerously close to Neptune's. Tyson and Kaku are both raising the red flag about a possible hazardous collision between these two planets, a collision that could pose a huge threat to Earth. Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even finished one full revolution. But the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the near-circular orbits of the major planets. What makes Pluto's orbit even more peculiar is its inclination. Angled at 17 degrees to the ecliptic plane, Pluto's orbit is much steeper compared to the other planets. This inclination and elliptical nature add layers of complexity to its orbital pattern. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question, why hasn't Pluto collided with Neptune? The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike the other planets whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricacies of space mechanics. The three-body problem in space explores how three objects such as Pluto, Neptune, and the Sun move and interact with each other's gravity. This interaction determines their long-term movements. Alpha libration. This means that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation prevents collisions. Latitude libration. This refers to the vertical movement of a celestial body. In Pluto's case, when it comes closest to Neptune, it is significantly above Neptune's orbital plane, providing an additional layer of protection. VZK oscillation, named after scientists von Zeipel-Kozai and Litt. This oscillation describes how the gravitational pulls of the Sun and Neptune influence Pluto's path, ensuring its long-term stability. These complex gravitational mechanisms help maintain the stability of Pluto's orbit over incredibly long time scales. Numerical simulations in the late 1980s revealed that despite these stabilizing properties, Pluto's orbit is technically chaotic. Minor deviations in initial conditions could lead to significant changes over millions of years. However, the unique properties of Pluto's orbit allow it to remain stable for billions of years. Recent computer models have helped us understand how giant planets Neptune, Jupiter, and Saturn affect Pluto's path. Neptune and Pluto share a special orbital resonance. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance keeps Pluto's path steady. Additionally, Jupiter's gravity plays a major role in maintaining Pluto's stability, with Saturn contributing as well. Without these stabilizing factors, the solar system would be far more chaotic, and celestial bodies like Pluto could be ejected from their stable paths, leading to a domino effect on other planets. Beyond its orbit, Pluto itself remains a fascinating world. The New Horizons mission, which flew by Pluto in July 2015, provided unprecedented data about this distant planet. Pluto's surface is characterized by thin atmosphere. Pluto's atmosphere, composed mainly of nitrogen, methane, and carbon monoxide, expands and contracts as it moves closer to and farther from the Sun. One of the most intriguing discoveries is the possibility of a subsurface ocean beneath Pluto's icy crust. If liquid water exists there, it raises questions about the potential for microbial life in such an extreme environment. Pluto is the largest known object in the Kuiper Belt, a region beyond Neptune filled with icy bodies and dwarf planets. Studying Pluto's orbital characteristics helps astronomers understand the migration of celestial bodies in the early solar system. Gravitational interactions between Kuiper belt objects and giant planets like Neptune and Jupiter can alter their orbits, sometimes ejecting them or causing them to collide with other objects. This interplay is crucial for understanding how planetary systems evolve. The ongoing debate: is Pluto a planet? Pluto's reclassification as a dwarf planet in 2006 sparked controversy. The International Astronomical Union's IAU definition of a planet includes 3 criteria. Pluto fails the third criterion, leading to its demotion. However, some scientists argue that this definition is too restrictive and should be reconsidered. The debate reflects our evolving understanding of planetary classification, future exploration, and implications. The New Horizons mission was just the beginning. Scientists are now planning missions to further explore Pluto and the Kuiper belt. Future spacecraft could analyze Pluto's potential subsurface ocean, its atmospheric changes, and its geological history. Pluto's orbit and its interaction with Neptune also have broader implications for exoplanet research. Many exoplanets have highly eccentric orbits similar to Pluto's, and studying Pluto helps scientists understand planetary formation beyond our solar system. Pluto's unique characteristics, its orbit, surface, atmosphere, and interaction with Neptune continue to challenge our understanding of planetary dynamics. While the idea of a Pluto-Neptune collision makes for an intriguing discussion, gravitational forces keep their orbit stable. As technology advances and space exploration continues, Pluto remains a key subject of study, offering insights into the past, present, and future of our solar system. The mysteries of Pluto remind us that the universe is full of surprises waiting to be uncovered. One of the most groundbreaking discoveries about Pluto is the possibility of a subsurface ocean beneath its frozen surface. Data from the New Horizons mission revealed that parts of Pluto's surface, particularly near Sputnik Planitia, show signs of geological activity, something unexpected for such a distant and cold world. Scientists theorize that beneath Pluto's thick nitrogen and water ice crust, there could be a layer of liquid water similar to what we suspect exists on moons like Europa, Jupiter, and Enceladus, Saturn. This theory is supported by tectonic features. New Horizons images show fractures and faults in Pluto's crust, which suggest that internal forces are at work, possibly caused by an underground ocean expanding and contracting over time. Sputnik Planitia's position, this large heart-shaped nitrogen ice plain, is aligned almost exactly opposite to Pluto's largest moon, Charon. This suggests that a dense subsurface ocean may have played a role in shifting Pluto's crust over millions of years. Thermal evolution models, computer simulations indicate that radioactive decay within Pluto's rocky core could generate enough heat to maintain a liquid ocean beneath the surface. On Earth, life thrives in extreme environments such as deep-sea hydrothermal vents and subglacial lakes in Antarctica. If Pluto's ocean contains the right chemical ingredients, water, organic molecules, and energy sources, it's possible that primitive microbial life could survive in this hidden world. The discovery of life on Pluto or any similar icy world would revolutionize our understanding of habitability beyond Earth and suggest that subsurface oceans might be common habitats for life in the universe. Pluto is not alone in the Kuiper belt. It is just one of thousands of icy bodies that orbit the Sun beyond Neptune. Some other notable KBOs include Quasar Sedna and other distant objects. These bodies orbit at the outer edges of the solar system and may hold clues about how planets formed. Even though Pluto lost its planetary status, it remains the largest and most complex object in the Kuiper belt. Scientists believe Pluto may help us understand how early solar system objects evolved. It is possible that Pluto, Eris, and other dwarf planets formed in a different part of the solar system and were later pushed outward due to interactions with Neptune and other gas giants. Further study of Pluto's composition, atmosphere, and surface activity can reveal insights into the early days of the solar system, a time when icy bodies like Pluto were abundant and shaped the planets we see today.